we can see that the sprinter's OBLA is reached much quicker than the middle distance athlete and the marathon runner, which shows these athletes have a greater resistance to fatigue and are therefore able to prolong the OBLA further. There are long-term training adaptations that a performer can undergo to delay their anaerobic threshold in their sport and muscle acidosis, so they can sustain their performance for longer to help them in their sport. As typically the athlete has the ability to delay OBLA wins or places higher in the competition or race. So from this we can understand that athletes working at a higher intensity and therefore without oxygen are going to produce lactic acid at a much faster rate than those who have oxygen, who are able to prolong the effects of fatigue. And we can see that it's quite a time that they can do that for, because the marathon runners are obviously working at steady state, their intensity is continuous throughout, so with oxygen the amount of hydrogen ions and lactate is sort of prolonged over the period of time rather than being produced in one straight instantaneous period. And as we spoke about the long-term training adaptations, this is also a strategy that athletes use in order to delay the OBLA, and we can see that the graph shows the participants' OBLA where the volume forces the performer's ability to generate the force to decrease the muscle acidosis because the insufficient amount of oxygen being produced to the working muscles, which we've previously mentioned. We can see here that the swimmer maintains a speed of 1.33 milliseconds and a lactate meters per second and a lactate level of 3.8 millimoles. But as the intensity increases to 1.4 meters per second, the athlete tries to maintain this pace, but more lactate is being accumulated until the performer is forced to fatigue around 22 minutes. We can see that as the speed increases, the quicker lactate is accumulated, and therefore a lower resistance to fatigue is then experienced by the athlete. So we can see that the athletes that are working below maximal and working at sort of steady state are much able to delay their OBLA and work at a longer period of time than those who work above steady state and maximal. They're much more limited to around 15 minutes in their performance because of the lactate accumulated in hydrogen ions. So the swimmer is forced to stop after 15 minutes. So we can understand that the maximal lactate steady state lies somewhere between 1.33 milliseconds and 1.34 milliseconds. So it is assumed that the lactate threshold or maximum lactate steady state is 1.33 meters per second. And that's sort of the maximum that they can work at. Here we also have another strategy that some athletes use, and this is soda loading. Now, soda loading is mainly used during high-intensity anaerobic sports where lactate has accumulated from the result of the glycolysis system, and the muscle's resistance to fatigue and supply of energy is compromised, as we understand this. So, if we look at this in an example, events like the 400 metres, 800 metres or 1500 metres that are endured for around 2 to 10 minutes, athletes in these events can use the technique of soda loading in order to try to neutralise the lactic acid in the blood to prevent the acidity from increasing to a point where the blood becomes too acidic. It is known as bicarbonate loading as bicarbonate appears naturally in the blood. It acts as a buffering agent to buffer lactic acid by ingesting sodium bicarbonate before an event commences in order to increase the bicarbonate in the blood. It becomes less acidic and more alkaline in order to help the athlete's anaerobic endurance by limiting the uptake of hydrogen ions and lactic acid. because as we understand, these are what result in the inhibition of muscular contraction, and where the muscles are performing insufficiently and the contractions are not being stimulated by nerve impulses at the demand needed, which leads to fatigue, causing the performer to not be able to work at the same intensity. It works with the mechanism of metabolic alkalosis as the body maintains homeostasis. The blood is maintained around a pH of 7.35 to 7.45, which is known as the acid-base balance. The buffering capacity is to do with how the energy is generated during anaerobic events. So, during the first 8 to 10 seconds, the fuel for muscle contraction is the stored ATP from the phosphocreatine ATPPC system. However, as we've said, around the first 2 minutes, the energy is then supplied by the glycolysis system. And we know that the end product of this is lactate because there's no oxygen present, which is then diffused into the blood. And also the increase in hydrogen ions as a waste product. This then results the pH of the blood dropping to as low as 6.9 and even lower in the muscle. And at this level of pH, the activity of phosphofructinase, which is the key enzyme in glycolysis, to greatly decrease. So this then inhibits the further production of energy from anaerobic metabolism and restricts it. And the acidity also affects the calcium channels, therefore impairing the muscle fibre contraction. And this is one reason why the amount of work that can be maintained at relatively high intensities is limited, because of the effect on these two factors. Since the increased acidity in the blood and muscles is the culprit, the idea of increasing the buffering capacity of the blood by inducing alkalosis is an idea that's been investigated previously. It led to the concept of using these agents, such as sodium bicarbonate, in order to diminish the acidity of the blood to an increase in anaerobic performance. The effect of increasing this bicarbonate is limited to the blood plasma, since the bicarbonate cannot enter the muscles. The concentration of this bicarbonate will remain unchanged, and the accumulation of acid in the muscles inhibits the fibre contraction. But the increased gradient of hydrogen ion concentration across the cell membrane increases the diffusion of hydrogen ions out of the cell, which reduces the acidity in the muscle. So in effect, the increased bicarbonate in the blood reduces the acid buildup in the muscles. And soda loading has this effect, and leading to increased performance. As we can see, we also have a graph to demonstrate the training with bicarbonate and how it increases endurance. And we can see that the time taken to fatigue in both groups, that it improved their endurance after their 8-week training program, because the group that had the bicarbonate had a much larger improvement, from around 400 seconds to about 1,200 seconds, than the group that just had a placebo, which went from around just under 400 to only around 900. So it shows that this is an effective method in a strategy in order to help increase endurance. And this is just building on the idea of lactate buffering, which we said how soda loading and sodium bicarbonate helps to sort of stop the blood becoming so acidic and therefore causing this muscle soreness from the hydrogen ions. Because of the glycolysis system, we've said that the lactate accumulation in hydrogen ions increase the acidity, and it's this idea of acidosis versus alkalosis, trying to make the blood more alkaline than acidic, so we can then remove these products much more easily. And we could just have a simple diagram here showing that buffering from the muscles and into the blood, which therefore results in carbon dioxide being expelled from the lungs, because this lactate is being converted into the products which are much more easily transported and broken down out of the body. So this lactate buffering just helps to move the hydrogen ions down the concentration gradient out of the muscle into the blood, so they can diffuse then from a higher concentration to a lower concentration. And we also have another strategy, which is known as glucose ingestion, which we will touch on a bit later. And here we have the strategy of glucose ingestion. And this is basically, within an exercise, the athletes will be using sort of glucose gels or sort of sports drinks that have glucose within them in order to help replenish their glycogen stores in the body. So carbohydrate intake during exercise can help to delay the onset of fatigue and improve performance of prolonged exercise, as well as exercise of shorter duration and greater intensity. So, for example, continuous exercise lasting around an hour and intermittent high intensity exercise like shot put and long jump and exercises like that. But the mechanisms by which performance is improved are different. And we can see on the left we have a graph which shows that the glucose ingested insulin rises, which causes the blood glucose levels to increase from normal, and we can see that the shape of the graph starts to rapidly increase until the glucose has met its peak, where the blood glucose and insulin are elevated. And this is where exercise starts, and we can see that because the glucose is taken up very quickly in the muscle because of the increased insulin and effects of exercise. And then we can see the blood glucose levels start to decrease quite rapidly, and if we're not careful we can experience something known as hypoglycemia, and we will look at this in more detail later on. And then we can see they start to increase again, but not to the point they were when it was high glucose levels. They return to normal, and therefore then exercise is sustained throughout. So during prolonged exercise, the performance benefits of carbohydrate ingestion are likely achieved by maintaining or raising the plasma glucose concentrations and sustaining high rates of carbohydrate oxidation. But during intense exercise, carbohydrate intake seems to positively affect the central nervous system, which supplies energy to the brain. So the amount of carbohydrate an individual athlete should ingest, there is no sort of set amount, is determined by trial and error, and a balance should be struck between increasing carbohydrate availability during exercise and minimising gastrointestinal distress, because we don't want to cause damage to our internal body parts. It's just helping us to give us a short burst of energy. So this is why you see in marathons the runners have glucose gels or the sports drinks in order to give them a quick supply of glucose. And on the right we have a graph showing a control group that didn't have any carbohydrates and a group that did have carbohydrates, and we can see that the group that had the carbohydrates, straight away that their glucose increased from around 5 to 7. And although it didn't deplete at the rate that the control group did. And we can see that they were able to sustain over around 150 minutes worth of exercise compared to the control group, who are only able to maintain exercise for a lot less because of the shape of the graph, how it decreases from around the glucose concentration from 5 to around 3.5. They wouldn't be able to sustain their performance. It shows that glucose has a real big effect on providing energy in order to be used over a longer period of time by the athletes. And this is a strategy that is used in order to help mainly endurance athletes in their performance.